the first part of the operating system we're going to spend a bit of time exploring is memory management. So memory is where we store running programs, the currently running programs, the instructions for it, the data that it uses, and the currently running operating system. So the operating system is responsible for managing how and where processes will have the data. So we're looking at two main methods in this video. So we're looking at paging and segmentation. Now, virtual memory is a big part of memory management, and I'm going to cover that in a separate topic purely because there's quite a lot of detail that goes into it. I didn't want to kind of mix and match at this point. And we're also going to look at the purpose behind memory management. Now, the operating system is responsible for managing the memory. So when we talk about memory, we talk about RAM, and as you know, we've got a von Neumann architecture, and data instructions are stored in the same place. Now, where that data instruction gets stored is the realm of the operating system. So the CPU is going to be fetching information. It's going to be connected to memory by a bus, but it has absolutely zero say in where things get stored. That is going to be done by the operating system only. Okay, so the CPU does not manage memory, it accesses memory. So memory can be considered one big continuous block. If you've already done arrays, you can think of it a bit like an array, where each item in the array will store one bit of data. Now, memory is going to be partitioned in order to allocate to different processes. So instead of just simply doing it byte by byte, because that can be quite inefficient, we basically chop memory into big chunks. So it's like you've got a cucumber, just like slicing it up into nice big chunks to give to people. So these partitions are then allocated by the operating system to different processes as and when they might require them. Memory is going to be secured. So a process cannot access another process. Now that's really important. I'll give you an example. So let's say I've got a process in Internet Explorer, okay, and I'm logging into my bank account and I'm typing in my password. Let's say I have another process. If that process could then come along and read the memory of the Internet Explorer, it'd be able to see unencrypted passwords as I'm typing in. So that's obviously a bad thing. So different processes cannot manipulate or change or do anything with each other's memory. Virtual memory is something we're going to be covering later, but again, just very briefly, it's where we use the hard drive or another secondary storage device as additional memory, and that's part of the purpose behind the memory manager. And really, one of the most important things is to allocate memory efficiently, okay, so that we make the best use of what is effectively a very finite resource. It's quite common for you to have more processes open that require more memory than is actually physically available, which is again one of the reasons why virtual memory is so important. So let's think of an example. So let's say I've got Microsoft Word open, okay? I'm writing my notes up for a computer science lesson. And I need some more memory. My Word document's gotten bigger. I'm running out of memory. I need more from the memory manager. So a request is going to go to the operating system. The system will then say, okay, so you need another block of memory. I'm going to decide you're going to have that block up there. Okay? So when a process requests more memory, the operating system will then allocate a new partition to it. The process has absolutely zero control about what partition again. In fact, the operating system might say, actually, no, you can't have another one, thank you very much, we're out of memory. So the application that's running does not control where or what memory it gets. That is the pure job of the operating system. So there are two main ways to partition this memory up to then allocate to processes. The first way is paging, and it's the most common way, the one that we're going to spend the most time looking at. So paging is one of the methods used to partition memory. It's where we split memory into equal sized chunks. So each partition that we split memory into is always exactly the same size. And the size of that is going to be determined by the operating system, and again, not by the applications themselves. Because of the fact that they're a fixed size, it might be that I need more than one. So in the example here, I got Microsoft Word, and it's using 2 partitions, and they've got Media Player, which is using 3. Now that's just one program. So what's had to happen is they've been split into 2. Okay, so they've been split apart, and a part of Word has gone into one partition, or one page, so to say, and the other half is gone into another. So they are physical partitions. We're physically splitting them up into chunks. Requests for large amounts of memory are always going to be split into multiple pages. Now, in order to manage which page is allocated to which process, we use something called a paging table. Now, I'm going to very briefly say what a paging table is, which is the mechanics of how the paging is actually done, but I would consider this as wider reading. It's not part of the subject clarification that came through, so I would consider this as wider reading, but it's an interesting way just to see how it's actually done. With the partitions in memory, we number them, starting at 0, going up to, we'll have however many partitions that actually can fit in. And that's physical memory. So we have each physical partition set up each page. Each process, however, will have its own kind of view of memory. Again, starting at 0. So both the physical one and the logical one both start at 0, but that doesn't necessarily mean that the application 0 is going to be stored in position 0 here. Okay. The reason for that is down to a number of reasons. 1, well, it might already be taken by another process. 2, if we can predict where a page is going to go, then maybe that's a security vulnerability. And 3, I might have copied it into virtual memory. So in order to know where each page for a process is stored, we use a paging table. So the paging table has the list of all the pages, and then the number of where it actually stored in memory. So position 0, so page 0 for the application is actually, according to the page table, stored in position 1. The second page in position 1 is stored over here in position 3. Okay, and then number 2 is stored there. Okay, so it's getting a little bit messy, but hopefully you're getting this idea. So the page table is a mapping between where the process thinks a page might be to actually where it really is located in memory. So it's time for a task to help maybe get some of this sinking in. So above here on the diagram, we've got a bunch of processes. I've named them A, B, C, and D. Okay, just to keep it short and sweet. Each page is 1 megabyte in length. Now, as you can see, I've got 2 free spaces. So we have a new process E, which requires 1.2 of RAM. Now, because it's 1 megabyte, we're going to need more than 1. So what I'd like you to do is describe, using this example, how process E will be allocated memory by the memory manager. Okay, so you're going to be talking about paging, and make sure you use the following words: partition, fixed, and physical. Now, paging is the most common way that we allocate memory, but there also is another way which is called segments. Now, segments are another way of partitioning memory, but instead of using fixed size blocks, we use different size blocks, variable size. So these allow a logical partitioning of memory. So if I, for example, had memory, like so, and I had a process which needs this amount of memory, okay, instead of actually splitting into 2 like paging would do, what I would do is just simply just kind of shade it in slightly, just put it straight into memory without doing any further splits. So that means that we don't have to partition up, and we can just simply slap it straight in. Now, if for some reason there is not enough space or free continuous space to store in, then maybe I will have to split it up. So segments, unlike pages, can also be shared, and this is one of the big differences, but we will set permissions on it to say which process can access it. So time to make some notes on this. So make sure you make notes on the purpose behind the memory management and the key differences and similarities between paging and segmentation. Now, just to finish off, here's the subject clarification. Now, this topic has been split into two. Okay, so the first one is looking at the purpose and what paging segmentation are. And then the second one is going to be looking in detail on virtual memory and then how paging virtual memory work together. Okay, so I've highlighted in red and underlined which ones this presentation has covered.